Hello, today, welcome to this talk. Ilya Vance Brundle came to this event to talk to you. It is his 6th Congress and his 4th speech, and you might remember him from last year when he talked about unusual web bugs. He's also involved in some kind of conspiracy with Dan Kabinski, and he will tell you something more about him right now.
So, thanks everyone for coming to Ilya's talk. I just wanted to say, my God, this guy is a crafty bastard. Ilya is the only person I know who ever has had a bug that does not work the first time, but then you try again. And it does not work the second time, and then you try again. No, you have to do the same damn thing 3 times, and then everything blows up. That is the kind of bug that this crafty bastard finds, and I hope you enjoy his talk now.
Okay. Because this thing's not working. I can just use the mic though.
Yes, it's on.
Is it on? Okay. Great. Okay. Hi, my name's Ilya. A correction, my talk last year wasn't unusual web bugs, it was unusual bugs. The talk this year was unusual web bugs, which apparently the style of it was based on what I did last year. So I'll be talking about a collection of random things. Look what I found on the carpet. In this case, dust mites. So who am I? I'm Ilya. I like to see things crash, and when it doesn't work the first time or the second time, it'll work the 3rd time, as Dan said. I work with Dan at IOActive. Top of that, I'm in a group called Metric, and I have a blog, which hasn't been updated in months, but I'm trying to change that. And I have a website, which has also been down for months, but that's not my fault. Okay, things I'll be talking about today. First of all, I'll be talking about race conditions in the usage of defkmm and how these things have security, what the security effect is of these. The second part I'll talk about are snprintf corner cases. snprintf is an API which is supposed to be a secure API, but really isn't. Third one is a bit more general than what's on my slides. It's pretty much general usage of out-of-band and interesting things you can do with it. Turns out one particular case of it is that you can avoid IDS. And then we'll get to TCP stack fuzzer stuff later. So, my talk's going to be pretty much along the same lines as I presented last year, although a few less things that I'll present in terms of items. Again, none of these things are big secrets. In fact, most of it is really old, obscure, and undocumented. These are things that people forgot 10, 20, 30 years ago. And I sort of looked under the carpet, and there they were. First of all, defkmm race conditions. What is defkmm? It's a virtual file, which means it's not really a file, it's just your kernel saying it's a file. And when you open it, pretty much what it does is it gives you access to kernel memory. Depending on how you open it, it gives you read and write access. In my talk, I'll only be talking about read access, but it's an easy way to poke into kernel memory. Among other things, it's used to get statistics, information about processes, networks, modules, load average, any kind of file script that's open, files that are open, any kind of thing that you couldn't usually get from userland. Because it's raw kernel memory, it needs to be protected, so by default, and you don't want to change this, only the root user can open it for reading and writing, and usually the group, and most of the BSDs KMM, can open it for reading only. If you have an application that gets information out of it, like netstat or pmap or PS or things like that, you will need a SGID binary, which sort of regulates what you can and cannot see. For those who don't know, SGID stands for Set Group ID, which basically means I'm running the application, but I'm running it as someone else. In this case, the group KMM. When you're reading stuff from defkmm, there's certain problems arise. The problem is that what you want to do is you want to read data from the kernel, but the kernel, pretty much, the thing is that if you want to read particular piece of data out of it, it will generally take you 2, 3, 4 reads in order to get to the data you want. The problem is that you could have had a dozen or a million or a billion context switches in between, and by the time you get to your fourth call, or your third or your second, the data you got from your first call could be invalid. And the problem is that you can't lock the kernel from userland with just cause, because if you would be able to do that, you'd have bigger problems. And so you end up with certain kinds of synchronization issues. So I have a very simple example, like if you write an application where you get these things. So let's say you have an application where you want to have the name of a certain process. What you would do is, well, first of all, you'd open up defkmm or defmem, and you'd go look in your symbol table and be like, well, where's my process table? And you find your process table, which is your first read. And then from there, you will have to go over your process table and find the structure that matches with the PID the process that you want to see. That's your second read. Now from there, in that structure that you found, will be a pointer which points to the name, excuse me, which points to the name of your process of which you want to get the name. And so you go and read that, and that's your fourth read. And you get the string, and then you print it. Now, this all sounds nice, but turns out that between step 2 and 3, where you read the process structure and you read the pointer from a particular process structure that you want, the one that you want to use, in between those 2 read calls, pretty much anything could have changed. For example, that particular process that you want to read data from may no longer exist, and so that piece of memory that used to hold the content of its process structure is now gone. And basically, the way that you could abuse this is between step 2 and 3, you get this process, you kill this process. The piece of memory it now points to is free, but the pointer held in userland still points to it. And then you do a certain operation where you basically regain access to that piece of freed memory, and you fill in the content like it would be a proc structure. But now you have full control over it. And so that means that the pointer that's going to be read, the process name that you want to get, excuse me, is now going to be a pointer that you fully control. And so you can have it point to anywhere in memory and basically dump that. And so that means you can arbitrarily and very precisely select parts in the kernel that you want to read, such as your buffer cache, because password files might be interesting, or TDYs, because who knows, maybe someone's SUing to root and might be able to sniff a password. Things like this. So that's pretty much the general idea of how these things work. Now, the race might seem small because even though it's a userland process, 2 read calls, there's not really much time in between. Maybe a couple of microseconds, maybe less. So you might think it would be hard to hit this race. But it turns out that it's pretty easy to make your race window arbitrarily large. And you can do this by sending a signal to whatever SID process you're trying to use. And the signal you want to send is sig stop, because it makes your process stop, first of all. And second of all, sig stop is one of the 2 signals which cannot be ignored. It will stop no matter what. At that point, it will stop indefinitely until you tell it to continue. And so you have all the time in the world to kill this process, regain its memory and kernel, and fill it out exactly the way you want it to be. Once all that's done, you just send it to continue, it'll start working again, and it'll start reading the pointer that you provided. And you end up reading any piece of kernel memory that you want to read. Turns out this issue has been around for a long time. Pretty much the day they decided that that's how we're going to do it, this issue was there. And this is probably 30 years ago. Like, you know, BSD has been doing this for a while. There's got to be people that know about this. And I'll talk about this in a second, but judging from their code, they sort of realized that you can have race conditions. They may not have realized that it was at security consequences, but they know there was a race condition. And so, stunningly enough, over the past 30 years, no one ever really raised a big stink about it. I spend a lot of time looking for any kind of reference where I could see, you know, someone said this could be a security issue, and I couldn't find it. But people sort of kind of realize that at least you have a race condition and you might have potential stability issues. And so people are switching to either using sysctl or the proc file system because these things lock structures in the kernel, and so you have no race conditions. And it makes much more sense. Linux pretty much uses the proc file system for any of these things. The BSDs will generally use sysctl. So yeah, DefKMM race conditions mostly seen in the BSDs. I'll sort of take a tour towards how NetBSD does it because that's where I looked. They have a whole bunch of applications installed by default that are SGID that will actually start reading data out of defmem or defkmem. The thing is, some of them will use defkmem, some of them will use sysctl, and actually, the majority of them will use both. They'll use sysctl whenever possible, and when there's a certain piece of information that they want to get for which there's no sysctl entry, they'll use defkmem. And in order to do this, it's sort of abstracted away in a library called libkvm. And so historically, it only used defkmem, and so at some point it started switching to sysctl. It's sort of kind of using both, depending on what kind of information you want. Most of the libkvm has a bunch of APIs that'll give you pre-processed structures that you might want to get, like someone's process structure, or the load average, or an argument vector of an application, or any of these kind of things. They've got like 20 or 30 of these APIs. I just have 3 on them on there. Now, they have one particular API called kvm read, which will basically just, you handed a file, you don't even hand files, you handed a descriptor to your kvm object. You hand an offset to where exactly you want to read, and this offset is pretty much your pointer in kernel. You hand it a pointer to data, and then you hand it the length, and it'll go read that much data for you. You can basically, before you can read, before you can call kvm read, or before it makes sense to call it, you have to call an open function first. And there you can specify whether either you want to work with the running kernel, or you want to work with a core file or your swap file, a bunch of things. These are the applications that are used by NetBSD that are SGID, and that'll, for any number of reasons, grab data out of defkmem. Any of these could be potentially used to leak arbitrary memory from the kernel. The interesting part about all these applications is that because they're running with elevated privileges, they try to drop privileges as soon as possible. And so you can drop privileges the moment you open your file, or the running kernel. And so they added code in there which does this, and which basically sees that if you're not going to look at the running kernel, and you're going to provide your own file, we're going to drop privileges before they open, because in that case, you don't need the kmem group. And if you need data from the running kernel, obviously they'll drop privileges after the open call. There's 2 applications where magically they forgot to do a priv drop. It's TRSP, TRPT. Both of these do not have priv drops, which is interesting because well, basically, the cool, I'll get to that next slide. So the interesting part about libkvm is that it's built under the assumption that it's getting all its data from the kernel, and so it'll implicitly trust this data. There's very little validation done. And so in one of the cases is where if you have this open file where instead of using the running kernel, it'll use a file you hand it, which is malformed, for example. libkvm breaks in a dozen different ways. And if you go for the running kernel with these race conditions, you can end up with the same thing where you can hit a lot of these bugs in libkvm. So the interesting part about TRSP and TRPT is that you can open a file you hand it, and it won't do the prif drop, and you can easily hit a bunch of libkvm bugs because it assumes that the data it's reading is trusted, and it's really just a file you handed it. Yeah, libkvm really doesn't stand up against random crap being fed to it. As you can see here, this is one of the Explorer APIs, which is kvm get files. And what it'll do is it'll read a number from the file or the running kernel. It'll, juggle some numbers around, add 10, multiply by something, and then add some header size, and and then you end up with your total size. Obviously, this suffers from a classic integer overflow. Your allocation will be too short, and you end up with a heap overflow. This is just one of the random functions in kvm that'll blow up if you hand it data that kvm trusts but really isn't. So when looking into this thing, I found some other issues. I was reading systat code in that BSD. And this is one of the apps that's SGID and reads data from defkmm. And it happens to have a signal handler, which isn't safe at all. And I went to compare with FreeBSD and OpenBSD, and they don't seem to have it. So either they never had it or they fixed it. I'm not sure. But this one particularly seems to affect NetBSD. This is basically what's happening. This is a signal handler called stop, which is called if you send the terminal stop signal. And they do this sort of weird thing where they set up their signal handler again and then basically put themselves to sleep, and then you have to wake it up again and they'll reset it again. And then they call redraw, which is basically a wraparound a bunch of incursus functions that'll free data and malloc stuff and open files and close files and do I/O and use a bunch of printf functions and stuff, things that are completely not signal safe. And so I wrote a one-liner POC, which if you run this in NetBSD, you'll end up crashing the application. Whether or not it's probably exploitable, I haven't had time yet to look into it, but you end up crashing, and there appears to be memory corruption. So this is pretty much a bug which should get fixed. I stumbled upon it a couple hours ago. This is what's happening. Basically, the code goes into an endless loop and keeps sending the signals until you hit your race condition, your signal race. And then I traced it, and you see basically you see the signals being reset, and it puts itself to sleep, and it wakes up, and it puts itself to sleep again, and it wakes up, and it puts itself to sleep again, and it wakes up, and it crashes. What? Yeah, from the slide, it's actually the third time. You're right. So when looking at kvm, I didn't have the man pages with me, so I had to go to their website and read it online. And when I see web forums, because recently I've sort of been nudged into doing some web stuff, and it isn't really my thing, but it's sort of growing on me. And so now, whenever I see a web form, my hands start itching, and I'm like, well, what happens if I put in a double quote or, brackets? And I did that too, and turns out they are filtering HTML data, but they're filtering it incorrectly. They're not doing HTML filtering. They're basically saying, well, let's add a backslash to it, because if that works in C code, it'll work for HTML, right? For those who don't know, it doesn't work in HTML, okay? I'm just saying. It supposedly, there might be corner cases, but supposedly it does work for JavaScript. Okay, so that was pretty much def KMM. Moving on to snprintf and sort of its corner cases. snprintf is supposed to be, or people are claiming it's the secure version of sprintf. They're right in that it's more secure than sprintf, and its behavior is described in the C99 standard. It's definitely more secure than sprintf. It's a lot easier to prevent memory corruption and buffer overflows. Excuse me. There's a bunch of corner cases, though, where if you use it incorrectly or in like certain nuances, things can go wrong. Some of these corner cases are implementation dependent. Some of them are pretty much a result of the spec and people assuming things that if sprintf does it, snprintf does it, and it's not really exactly the same. So first of all, snprintf's return value. When successful, it'll return the data that was put into a buffer. However, because it does a bounds check, it's not going to tell you how much you put into the buffer. It'll tell you how much would have been in the buffer if the buffer was big enough. So people would assume, or a lot of developers assume, that it'll give you how much was written in the buffer and not how much would have been written. And this turns out that you can do a lot of things wrong with it, and I'll get to that in a couple of slides. The other thing is that snprintf guarantees no byte termination, except when you put in a length of 0, which makes sense, because otherwise you end up with memory corruption. But there are interesting cases where you can get something to arbitrarily malloc a length of 0, and then you do an sprintf 0, and then you assume it's null terminated, but it really isn't. And so you end up leaking some memory, and depending upon what you do with that, that may or may not be a problem. So most people don't know this, but snprintf can fail. It can just not do what you ask it to do, in which case it returns -1. So the spec pretty much leaves open what happens if it fails. It's not guaranteed to be null byte terminated, so you might end up not catching that it fails, and then you have a string that's uninitialized. And again, depending upon the situation, this may or may not cause problems. And this is kind of common because very rarely do you see people use snprintf and check the return value, and you really should. So yeah, return values get abused. First of all, if we go back to the case where it returns where it returns what would have been written if there was a bounds check, quite often what people will do is they'll do pointer plus whatever snprintf returned, and so you end up with increasing your pointer beyond where its buffer ends. This is generally where you have a pointer and then plus equals snprintf pointer size and then your format string. And then you basically, and generally these things happen in a loop. So the first time it'll be right, it'll work. The second time you end up doing memory corruption. The third time it'll be memory corruption. Basically, you're screwed from the second iteration if you do this. That's if snprintf succeeded. Now, if snprintf failed, and you're not handling the error case, your pointer actually gets decreased by 1. And again, if you're in the case where you're in a loop, it'll get decreased by 1, and the second iteration will get decreased by 1 again and again and again. And suppose you have 200 or 300 iterations, you just decreased your pointer with 300 bytes, which may very well allow you to corrupt memory. So, how do you make snprintf fail? Turns out that in Linux under glibc, under certain locales, I think I missed an E there, snprintf will actually try to do Unicode conversion. And the spec leaves this open. Why not do this, right? And so if you hand it broken data there, snprintf will say, whoa, I'm not going to handle that. And it'll just fail, return -1. And so you end up back in the case where you have this loop, and you end up decreasing a pointer. The other thing is that because of this Unicode conversion in certain situations, you can bypass certain filters. Let's say you have an application which tries to make sure you're not doing a directory traversal, and you just pass it some data which looks like garbage but is not a directory traversal. That's fine. And then pass it on to snprintf, and it turns your Unicode garbage into ASCII directory traversals, for example. There's probably many more cases where you can do this, or similar effects for this. Last thing I want to say about snprintf is that it's sort of encoding 3 different kind of things into a single return value, which is kind of silly. I mean, it's confusing. Really, you want to have this thing where you can be very consistent and say, look, it's either right or wrong. And it's not just snprintf. You have a lot of APIs out there that are pretty, there was no thought put into the design of these things, or not enough. And you end up with these things where you have 3 or 4, you'll have a return value which says this is correct, or this is correct, but there was some bound check, or it's not correct and we totally failed, or it's not correct because of the stars didn't align and something like that. So it's not really a bug, I guess, but I find it very sloppy, the sign of very sloppy design. And it doesn't just affect snprintf, it affects a lot of APIs. Oh, right. So when I was testing this stuff on Red Hat Fedora Core 7, I was like, why is this thing not working according to the spec? I'm not drunk, I'm not tired, or I wasn't back then. And I go over my code again and again, and it keeps giving me so the C99 spec basically says it can return you wrote this many bytes, or you would have written this many bytes, or it can fail. And what Fedora Core snprintf does is no matter what you do, it will always return the exact size you gave it as input, which completely breaks the standard. I don't see how they can get away with it. I know at the very least it breaks TCP dump for certain dissectors. I was stunned when I read this, and this is clearly a Red Hat bug. This can't be anything else. Yeah, they should. I don't know. I haven't checked Fedora 8 yet, but this should get fixed, and was really a pain in the ass to work with because I lost a lot of time on this. Wow, this will be a short talk. Okay, nearly last part of my talk is the usage of out-of-band data, and really I'll talk about more than IDS evasion, but in certain instances you can use it for IDS evasion. So what is out-of-band data? It's basically a way that you can, in TCP, you can signal for some data. Generally, it's called urgent data. You really want to get something through. The way it happens is, if you look at your TCP packet, there's a flag which gets set, and there's an element in there called a pointer, which is really only an offset, and it points to somewhere in your packet. Generally, it'll be 1 byte before the last byte of your packet, and it'll be the 1 byte, which is your out-of-band data, and you basically get 1 byte per packet. It's somewhat an austere feature. It's not really used anymore these days, but it's still supported everywhere. And most people really don't know how to use it, or think they do, but really don't. Basically, most people rip their description off this stuff, of the Stevens books, and they sort of rape the description. It's not what it's supposed to be. Just go read Stevens and he'll tell you how to do it. But I'll give it a shot anyway. Sending out of band data itself is actually really simple. You call your send API, you give it normal arguments, your file descriptor, data length, and then just say, set, out of band. That's it. That's it for sending. Receiving is a bit more complex. It depends what you want to do and how you're going to do it and how your defaults work. Because it turns out that your defaults, even though there's a certain standard, the defaults of different operating systems are not what they should be. So by default, what should happen is nothing. This data you'll send it, but if your app doesn't register it and doesn't tell your kernel it needs it, it really won't. Really nothing will happen. Basically, it'll queue the first byte, and then when the second out of band comes in, it'll basically throw out the previous one. So if you want to somehow handle out of band data, you got to let your kernel know. And the way you do this is you say, look, I have this socket, and I'm expecting out of band data on it, and I'm this process, and here you go, and connect it to, and every time on that socket you get out of band data, send a signal to this process. And basically you call fcntl, or there's also an ioctl for this, and that's exactly what you do. You pass in your file descriptor, you pass in your PID, and that's it. You're done. To the point where your kernel now knows that you want to get out of band data. How you want to handle it is something else. Once that's done, whenever you get out of band data, you'll get it. Now it depends on how the kernel will give it to you. By default, it'll signal you that it's there, but it won't just hand it out to you. You'll have to receive it and then specifically set the out of band flag again, which is pretty much the equivalent of the send of out of band. Now, what you can do is you can say, you know what, I don't want to go through all this hassle, let's just put it in with the auto data. And you can set a socket option called out of band inline, and that's basically what will happen. Now, on Linux, things or used to be a bit different. Basically, what they did is they took everything inline. It's like, I send you out of band data, and you get it inline. So this sort of is not what it's supposed to do, but it works generally because no one uses out of band data. But your IDS doesn't know this. So you can smuggle in data through out of band, and your IDS will just be like, it's out of band data. Apparently, newer 2.6 kernels don't do this anymore. I've been trying to hammer on them, and I couldn't get them to do it. But I know older kernels do allow you to do this. There's a bunch of other things that you can do with out-of-band data to try and avoid IDS detection. Because the thing with out-of-band data is that there's no standard on how you're going to use it. It's very much application dependent. You can ignore it. You can have it inline. You can have it signal to you. And there's no way for an IDS to know how you're going to handle it. Are you going to ignore it? Are you going to catch it? How are you going to catch it? The IDS doesn't know. It can't know. Unless it's running on the same box and it's inspecting your process, it can't know how you're going to handle out-of-band data. That's about it for out-of-band IDS evasion. There's a couple of other interesting things with out-of-band data that are actually rather old, and so most people forgot about them, but they're pretty much a known thing. So earlier I talked about that you have to tell your kernel that you want to receive out-of-band data. And the way you do it is you link your file descriptor or your socket with your PID. Now it turns out that there used to be these bugs where you would link your file descriptor with someone else's PID. Let's say a process not owned by you. And your kernel would basically, upon receiving out-of-band data, will send the signal to this other process. So you just ended up with a situation where you can send a signal to a process you're not supposed to send signals to. Now, whether or not that's a problem depends on the implementation of whatever process you're sending data to. But I can certainly imagine situations where this can cause problems. So this is fixed in most Unixes. It's been fixed for, I think, about a decade by now. So it's rather old. I believe the OpenBSD guys came up with this. I'm not entirely sure. But who knows? It's this old. Maybe someone missed it back then. Maybe someone reintroduced it. You know, my bet is that there's going to be a couple of operating systems out there where this will still be an issue. Another out-of-band issue, which has been very well covered by Michal Zalewski a couple of years ago. And before that, it was sort of got slight attention in 1997 with a bug in WIF2PD. But basically, the thing with out-of-band data is that if you have an application that says I want to handle it, it gives you the ability to remotely send a signal to an application, the urgent signal. So it's this one particular signal. And so depending on how the signal is going to be handled, it might cause problems. Because as it turns out, in Unix, doing signal handling is a very tricky thing. Pretty much everything you do in your signal handler has to be, in total, has to be atomic. If you have two different operations where one would be atomic and the other one is two, but in between there's something, that will still cause problems in signal handlers. And there's a lot, I'm not going to go into it, but there's a lot of things you can do wrong with signal handlers. And Zalewski did a pretty good write-up on that, and the OpenBSD guys had a pretty good presentation on that. But believe me, if you can send a signal remotely, that's generally the applications will screw it up somehow. It's very difficult to get these things right. Somewhat related, a buddy of mine, actually a colleague of mine, Justin Ferguson, told me that there's another way where you can remotely send a signal to a process in Linux. It's kind of tricky and it sort of depends on the situation, but basically you have this thing called the out-of-memory killer in Linux. And what that does is when you're running short of memory, it sort of goes down the list of processes and says, well, which one's the bad guy here? And first it'll send, I think it's sigterm or something, or sigint. And then when you're not responding, and I believe when you're not root, eventually it'll kill you. But initially it'll send you different signals. And so this means if you can remotely start consuming lots and lots of memory, you can basically remotely trigger these signals to probably process where you get some influence in, probably the process that you're getting to consume lots of memory. Okay. These are basically links of out-of-band data. I missed one in there. I'll have to update my slides. So, I was going to present on a TCP stack fuzzer, and I had actually written a lot of code on this. But, you know, I'm kind of a slacker, and I had Christmas parties to go to, and flying back and forth, and some work here and there, and I have lots of code written, it's just not functional. I'll have to get back to you on that. I'm definitely going to finish it. Maybe next year. It's going to come out, just not today. Yeah, that was actually it. Any questions? No? Oh, crap. Does anybody have a mic to go to these people?
Hello?
Oh, right, okay, sorry. My glasses suck.
On your presentation of the KMEM race condition, you said...
Can you speak up a little bit?
Okay. On your talk about the KMEM race condition, you said that if you had, by this by this race condition, you could read out arbitrary kernel memory.
Yes.
Have you really exploited this? Because it's not obvious to me how you could use this, because you wouldn't know what memory it is. It's kernel memory.
Okay, you're talking a little bit not loud enough because I can't really hear you. But wait, from what I understand, is you're asking if I've actually exploited one of these?
Yes, because it's not obvious to me how you could use the memory you read it out, because it seems arbitrary to me.
Okay. No, I haven't written a full exploit for this yet. I was kind of short on time, but I am going to make one. And if you want to be informed on this, leave me an email address or something, and I will get back to you on this. From what I know, it's not as difficult as it seems. It'll depend on how you allocate memory and free it. For example, let's say you have this where I went over these 5 steps. And let's say if you have a pool of these processes, it might not be that easy to randomly get access to it. But if you just have a normal allocator with malloc and free, where you really don't have any pools, it wouldn't be that easy, but it'd be realistic to trigger these things. And you have to keep in mind that you can your race window is arbitrarily large. So this means I can keep trying and keep trying and keep trying a billion times, and I can keep trying for a year until I get it exactly right.
Okay.
Does that answer your question? Okay, thank you.
Hi. In the libkvm you said you can have fun with self-made score files.
My classes really suck. Wave at me. No, the guy is talking.
Hi.
Okay.
You said in libkvm there are some bugs you could exploit with self-made core files. Is there any way to force these setuid or set group ID programs to use your core file?
Wait, can you say it again?
Can you force these programs to use your core file instead of the kernel memory?
Yes, you can, and I actually talked about that. So this involves the privilege dropping. So you have to find an application where you don't do privilege dropping and take a core file. Now, most of the applications that they're using, they have the right priv dropping installed, and so yes, you can give it a core file, but it won't give you any extra rights. Now, there's two exceptions. There's TRSB and TRPT, and these two don't drop privileges. So for these two applications, yes, you can hand it a core file, and if it blows up on something and it's exploitable, you can gain an open file descriptor to defkmm and the group kmm. Does that answer your question?
Do these programs usually operate on kernel memory, or is it a normal option to give them the core file? Or you have to trick them?
You can give these applications your core file.
Oh, okay. That's good. Thank you.
Just for the record, those 2 programs have been removed 6 months ago with the rest of the NetNS support, simply because it was extremely horrible code. And believe me, those 2 programs are not the biggest issue in the code. So
I know because I checked a couple hours ago. One of them got moved. One of them is still there. I checked the
they
CVS.
should both be dead. Okay,
I'm
the other
pretty
one will
certain.
be removed otherwise.
I believe, I'm not sure, I think TRSP got moved and the other one is still there.
I couldn't find it. I looked, that's why I'm curious. Well, this that will be fixed.
Okay.
Well, but you're sure invited to tell us about the more significant problems in the kernel.
What?
So it seems pretty interesting that you can do sig stop and sig continue to set GID, and I assume set UID apps as well.
Yes.
Have you seen a large number of like time of check, time of use bugs where you start the set UID app, stop it, change whatever it's working on, and then continue?
Yeah, this is pretty much one of there's a couple others. This is the biggest trick to arbitrarily open your window. This is like the #1 trick. It's like whenever you see these things, that's the first thing that should come to mind. There's a few other to try and install things and to try and pinpoint, because the thing is you can send sig stop and sig continue all you want, but you don't know exactly where you landed. And so you need a second trick where you can sort of pinpoint where you landed. And on Linux, for example, in proc, you can actually see when it sig stops, you can see the instruction pointer. And if you know the instruction pointer, you know exactly where you landed.
Is the proc file system entirely atomic? Like, can you not interrupt anything inside of proc? Or can you do any weird tricks there as well?
I'm not sure. I know the proc file system doesn't suffer from these kind of race conditions because at the very least they can lock in the kernel. If it's atomic, it depends on what you're trying to read from proc. I'm guessing no in general. There might be certain situations, certain files where it might be, but in general, my guess would be no. I'm not certain though. Okay. That was it? Okay. Thanks for listening.